of signed graphs, of course. But because signed graphs is somehow not a new concept, but something we are not necessarily familiar with, I will describe more precisely what are signed graphs in a slowly way. And so please do not hesitate to ask a question if you have any. So signed graphs goes back to, say, in the 40s, Harari did some work on signed graphs. So signed graphs is not really a new concept. But what is new is this notion of homomorphisms of signed graph. And so it is so new that the vocabulary and the notion are not clearly defined. Yes, clearly defined, yes. But there is no standard. And so I will give you the latest definition of homomorphisms of signed graphs. So let me start with this notion of signed graph. So what is a signed graph? It is a graph. So G is a graph. So usually we just deal with simple graphs with no loops and no multiple edges. But here I will speak about general graph. So we may have parallel edges. So this kind of thing is allowed. And we may have loops also. So this is a pair with a graph, such a graph, and a function. So this function just associate with each edge of the graph a sign, which is either a positive or negative sign. Okay? So it is some kind of two-colored graph, two edge-colored graph, as Chagnik discussed before, but it is not really colored. This is signs. And so with signs, you can do some operations. So this is a new thing somehow. So this is a signed graph, for instance. These two edges are positive, equipped with a plus sign, and this one is a negative edge. So for negative edges, I will draw with these dotted lines. So this is a signed graph, okay? So the next important notion is resigning. So Chagnik already spoke also of resigning, switching, pushing, but this is not exactly the same definition. So the idea is the following. You take any graph, any signed graph indeed. So for instance, this one. And you take a cut in this graph. So what is a cut? It is a set of edges. So here I have 3 edges, which separates the graph in 2 parts. Okay. And so we are here resigning at a given cut in a graph. And so a cut is just given by the 2 sets of vertices. Of course, y here is a complement of x in the set of vertices, of course. And so resigning is what you can imagine. We just change the signs of all these edges. And in this example, so the left part is the same, the right part is the same, of course, but we just change this sign. Yes. Okay? So this is resigning. So sometimes one of these 2 parts is only one vertex. For instance, if you consider this cut with one vertex for this part, then resigning is exactly what Chagnik was speaking with. Just changing the signs of all edges incident with this vertex. Okay? So this is the same concept. There is nothing really new.
So that one is pushing one
yeah.
part of the cut.
And of course, you can observe that if you modify the size at each vertex of one part, you get the same resigning. So this resigning is just a set of vertex resigning, nothing more.
Missing one thing.
Yeah.
You can change the sign you want, or?
No, you just choose this particular set of edges.
Signs are given with you, right?
Yes.
It's part of the input.
Yes, part of the input. You are signs.
Okay, okay.
Yeah, sure.
And then you are making this number.
Yes. So you give me signs, a graph with signs. I choose one cut, and I modify the signs. Exactly. Yes. Okay. And in the theory of signed graphs, but I will go into more details later, these signed graphs are considered as equivalent. So you can say these two drawings are equivalent, but somehow as a signed graph, this is the same signed graph. So this drawing and this drawing represent the same signed graph. Okay, so there is some kind of equivalence relation behind. But this is the same signed graph, but the two signings are equivalent. So I forgot to mention that this function is called the signature of the graph, of course. So sigma here is called the signature. So, okay, resigning is really important, so you have to get it properly. So, when an edge is colored with plus, I will say that it is a positive edge and a negative edge. But you can also speak about a positive subgraph or negative subgraph, a positive path, a positive cycle, and so on. But what is a positive subgraph? You take a subgraph and you compute you multiply all the signs. So if you have an even number of negative signs, you get a positive subgraph. And if you have an odd number of negative signs, it is a negative subgraph. So the next notion is important because we are allowing multiple edges and loops. So I will speak about. So how do you multiply? Yes, minus by minus is plus. No,
loops. For loops, how many times do you? So is it a negative loop?
No. If you consider this as a loop, as a subgraph, it is a positive loop, but with closed walks, you are going. You may take 3 times this loop, and yes, but only one negative loop is a negative subgraph. But if you go twice this loop, you get a positive. So this is closed walks, of course. So this is why we use this notion. So closed walk. So just what is a walk first? So a walk in a graph, in a signed graph, but in a graph in general also, is just a sequence. So a walk of length k. So the length will be the number of edges in the walk. So this is a sequence U0, E1, U1, E2, and so on. U k minus 1, ek, uk. So U0, U1, and so on are vertices, E1 and so on are edges. And of course, if you consider the edge EI, it goes from U sub I minus 1 to UI. So we are just working in the graph, but we use this notation because of parallel edges. When you have 2 parallel edges and you go from this to this vertex, you have to say which edge you are taking. So this is, of course, why we use this notation. If you just deal with simple graphs, a sequence of vertices is enough, even if we have loops. If you have loops, but if you have multiple loops or multiple edges, we use this notation. So this is a walk, and of course, this is a closed walk if U0 equals UK. Of course.
There can be repetition of vertices.
Yes, there is absolutely no restriction. So such a walk is a path if you don't repeat any vertex. And this is the same for cycle. A cycle is a closed walk so that you do not repeat any vertex except the first one, of course. So this walk is closed when the first and last vertices are the same. Okay? So you understand what is the sign of a closed walk. You just consider the edges and you multiply all the signs of these edges so that if some edge is used 3 times, say 3 times, then each sign is multiplied 3 times. So you keep the multiplicity of each edge. Okay? So we have 4 types of closed walk. Because you can consider the sign of a closed walk either positive or negative, but you can also consider the parity of its length, either even or odd. And so you get, in such a way, 4 types of closed walks. So we use this notation. We have 4 types, which are 0, 0, 0, 1, 1, 0, and 1, 1. It's not from a computer science point of view, but just a group theory point of view. So this one means positive and even length. So an even number of edges and the product of signs is a plus. Okay? And you can complete. This one is positive odd length. And the last 2 are negative even length and odd length, of course. So if you try to remember which signs correspond to sign or parity, just remember that when you write a negative number, you write a -8. So the first is a sign and the second is a parity. So it's a good trick. I hope so. Because this is quite strange, but I myself, I don't remember, so I use this trick.
But you made this convention.
Reza decided, and now I explain how to remember. Yes, I forgot to say, of course. All these notation, new notion are rising from discussions with Reza, Clément, Chagnik, Tom Zaflewski, and so on. Several people which are working on. So this is why it is some kind of moving theory at that time. It's not completely, and there are a lot of different terminology in several papers. So I try to somehow unify or fix some things. So, you probably know what is a girth in a graph. This is just the size of the smallest cycle. So if you take an ordinary graph with no triangle, it means that there is no cycle of length 3, and the smallest cycle, if any, has length 4. So we say that the girth of such a graph, a triangular graph, is at least 4. So with cycles, you can define girths. With closed walks, we can also define some kind of girths, but we have 4 types of girths. So 4 types of closed works gives 4 types of, I don't know how to say, I would write closed walk girths. Okay. But I will say girths probably, but I am dealing with signed graphs. So of course you get these girths, G00, G01, G10, and G11. So let me just repeat. For instance, this G10, so G10 of a given sign graph G sigma, so a graph with this sign function is just the smallest length of a negative even closed walk. Negative even closed walk. And of course, maybe there is no such walk in this graph. And in this case, we just set this value to infinity. So it is infinity if there is none such walk. Okay? So this is not easy to deal with at the beginning. You have to be concentrated somehow. So for instance, one easy question. What is the value of G00 of a signed graph? So what does it mean? You have to find, you take any signed graph, your favorite signed graph if you have any, and you just, what is the smallest length of a positive even length closed walk? Two. Sometimes. So half of the answer, of course.
No, but you are talking of simple graph. Yeah, simple graph is not going. So if you have one edge, at least.
Yeah.
Oh yeah, you walk.
Yeah. Yeah. Yes, there was a trap. So one edge is this is a closed walk, of course. So if there is an edge, the answer is 2. Yes. Yes. So you get only 1/3. But now we have at least 2/3. So the last one is? Yes, and then infinity. Yes, you're right. So it is either 1, 2, or infinity. 1 if there is a loop. 2 if there is no loop but an edge. And infinity if it is an empty graph, so a graph without any edge. So this girth is not really interesting, of course. So we are just dealing with these 3 values. Okay? So we just forget this one. There's no special interest. So I will just show you a few examples just to say that if you consider the size of the smallest closed walk with this property, it is not the same as considering the small cycle, which means that this girth is not necessarily attained by some cycle. So let me give you, so now you remember the trick. So sign first.
That 2 was such an example. If you just have one edge,
Yeah.
then it's not part of the cycle.
Yes. Yes. But there are also some kind of weird example. So let me consider, for instance, I will just, oh yeah, 3 examples. So So because I don't want to try every girth, we consider this one, G10 here, G11 here, and G01 here. So consider first this sign graph. So I want to find a closed walk or a cycle which has negative sign, which means that the number of negative edges is odd, but the length is even. Okay? So there is no even cycle somehow here, but there is a closed walk with an even number of edges when you do this. Okay, so every edge is in the closed walk, and there is only one negative. So this is clearly a closed walk which is negative of even length, and the length is 6 here. But there is no 6 cycle. So 1, 1, I mean, again, yes, again a negative closed walk, but with odd length. So for a cycle, you have this one. Yeah.
So in the first case, white is not 2. So because negative.
Oh, this is a yeah.
But it has to be odd.
Yeah, because of no, but it is important, of course. The edge is some kind of degenerate example, but it is always positive. If you take a negative edge, minus, minus, you get a positive closed walk. So it is always positive. Yeah. So this is yes. So G01 is not 2. Is not as simple as this one, because every edge or loop. No, not for loop. Ah, yeah. For loop, I have to exclude it. Yeah. Negative loop is not interesting, but it is in the definition, so I have no negative loops. Yes. Okay, so G11 means negative closed walk of odd length. So you have to take this 7th closed walk, and you get 7 here. And in this one, you again, the 7 will work, which is a positive closed walk of length 7. But if you take a shortest odd length closed walk, you have the triangle, but the triangle is negative. Yeah, it's not positive. And there is no 5. Okay, so again, it is 7 here, and this is not a cycle. Okay, so you get these 3 notions. Where?
Triangle plus an edge will be 5.
1, 2, 3, 4. Yes. Yes. So it is a pedagogical talk, of course. This is what you ask me to give. Yes. Okay. This is no. I am odd here, so it's okay. Odd. Okay, so this will be important when I will define homomorphisms of sign graphs. So this is why I focus on this particular definition. So the next point, just before going to homomorphism, I guess. Yes. It's about equivalent signatures. Yeah. Again? Which one? This one is 7 also? So why? Oh yes, because it is not. Yeah. It's a very pedagogical talk. Yes, I forgot. correct. I will keep it on the blackboard for a moment. So, we have seen with this resigning operation that we can get some kind of equivalent signature. So I will say that two signatures on some graph G are equivalent. If and only if. So when you consider the first signature and the second one on the same graph, G, then you can go from one to the other by doing this resigning. So which means that there is some cut somewhere, such that if you change the signs of all the edges of this cut, then you get the other signature. And of course, it is an equivalence relation. And so in terms of sign graph, you can consider that these two representations, these two signatures, correspond to the same sign graph. Okay? And so there is a theorem of Oblonsky which says how can you decide whether two given signatures are equivalent or not? And so this, I would say, a lemma, which is due to Oblonsky in 82. We say that sigma 1 and sigma 2 are equivalent if and only if these two sign graphs, G sigma 1 and G sigma 2, have the same set of, in the terminology as used, say negative cycles. So you consider these two sign graphs given by these two signatures, and you just look at the set of negative cycles, and they have to be the same. And so it is one direction is easy to see, because when you resign at some vertex in a cycle, you does not change the sign of the cycle. And so this is some kind of permanent property of a cycle. So you can replace cycles by closed walk, of course. The lemma is still correct. And in the terminology of the previous work, this negative is also called unbalanced. So there is two equivalent terminologies here. Negative is unbalanced, positive is balanced. Yes, so unbalanced, and this is not the same. You will see some differences somehow. Big? No, not so big. Okay, so this is somehow an important result. And so, because negative cycles, or unbalanced cycles, indeed, are important structures when you are studying sign graphs, we have some notation with U of unbalanced. So UCK is just the unbalanced cycle of length k. So unbalanced, which means negative cycle of length k. Okay? So this is correct. I can erase now. So for instance, one particular cycle of importance is this one. So for instance, you can draw it as this one. But you can also consider that you have a 3 negative edges. But these two signatures are equivalent. So this is two signatures which gives you the unbalanced cycle of length 4. But this is the same sign graph. This is just two ways of drawing this graph. Okay? And in fact, because of this, you can consider that the unbalanced cycle of length k, this is just a cycle of length k with one negative edge. Every other representation is equivalent, of course. Okay, so I think that the material is ready now to define homomorphisms, which is a key point of this meeting. Okay, so up to now, if you have any question on this notion, maybe before giving you homomorphisms, it's okay? So let me turn to homomorphisms. So Chagnik spoke about graphs, edge-colored graphs, oriented graphs, and he uses some definition. Yes, and so homomorphism, as defined by Chagnik. So if you consider just ordinary graphs, so simple graphs, no loops. So for instance, so it says that homomorphism H from G to H is a mapping which maps the vertices of G to vertices of H, such that whenever you have an edge in G, the image of this edge, so Hx, Hy, must be an edge in H. So this is the definition you gave, which is a correct definition, of course. If you have loops, it's correct also, because you get XX and Hx, Hx, if there is you must have a loop. But if you have parallel edges, it doesn't. It is not clear. So in some sense, you have several choices, so it's not clear. Yeah, it's not clear. I think I'm not sure. We can discuss. It's not. So I will give an alternate equivalent definition, but which is more which works fine with multiple edges, of course. So I just consider ordinary graphs for starting because it is easier. Everyone has this kind of graph in mind, so you can check the definition. So I define such homomorphism using two mappings, one for vertices and one for edges. So I map vertices to vertices, edges to edges. I can use the same H, it's not important. We know about what we are dealing with, but the condition now is that if W is a closed walk in G, then its image is a closed walk in H. Okay? No? What? What do I need? What? For every, we don't know? Yes. Yes, because we have seen just before, we have discussed that an edge is a closed walk. It's a closed walk of the same sign. No, it is graphs. Sorry. Yeah. I am not with sign graphs yet. Yes, but this is a mapping, so the number of edges is the same. But you're right, you have to observe this. The length is obviously preserved, so I don't need to say it's the same length. Okay, so because each edge is a closed walk, every edge is preserved also. Okay, every loop is preserved, and so on. So this is nothing more. This is just another way to see the same notion. Yes, because of this mapping, it is more precise somehow. Okay, and of course, when later we will use signs, it may be important to know which one. If you have a parallel positive and negative edges, the things are not clear. So this is why we use these two mappings instead of one. And this one is nice because we will use it. Okay, so this is clear for graphs. And so this is the same for sine graph. So if I put here sigma and say pi of the same sign. Which means something strange somehow. But strange and interesting. So of course you are, all of you have in mind that these edges, can I map a negative edge to a positive edge? Yes. Yes, because a negative edge, tac tac, this is a closed walk which is always positive. And you maps to a positive edge, which corresponding to walk is also positive. So it is, of course you can do that.
But it's no more a function, right?
Sorry?
Edge mapping, if you want to preserve edge mapping, then will it be a function? An edge which is mapped to an edge.
Yes, yes. Yes, yes. These two are function.
So
I mapped.
only an edge mapping. So
But there is no condition on this edge mapping. I don't say a sign preserving edge mapping. No, no. Just an edge mapping. Okay? If you consider the other type of graph, for instance, two-edge colored graph with red and blue, in this case, we use a color preserving edge mapping. A blue edge has to be sent to a blue edge and so on. But with sine and this resigning operation, this is not so fixed. So you may send a positive edge to a negative one and a negative one to a positive. For instance, an interesting example is if you consider a tree, for instance, this one, you can send such a signed graph, for instance, to K2. Either positive or negative, say K2 just. This is allowed, for instance. So I will just clarify the mapping. So I will use two names here, 1 and 2. So the name of the vertices. And I will show you the vertex mapping, which is enough, because I have no parallel edges here. So 1, 2, 2, 1, 1, 2, 1. Okay, this is allowed. So if you are reading previous works on this notion, the definition is slightly different. So the first definition of homomorphisms of signed graph, so the first one, only for simple graphs. Maybe to be checked, but say only, it was defined for simple graph. Yeah, maybe it works, but it was defined for simple graph. Is that if you want to have a homomorphism from G sigma to some H pi, you are allowed to resign first. So you get some sigma prime, a new signature, but which is equivalent to the first one. And then, when you have done this resigning, then you use a 2H colored homomorphism, a sign preserving homomorphism. Okay, so here you have a sign preserving homomorphism, which only means that it is a standard homomorphism, but when you are mapping edges, you preserve signs, positive to positive, negative to negative. And so in this example, if I am using the previous definition, I have an intermediate step, which is this resigning operation. And so the idea is that it is not difficult to observe, and we will observe it on this example, that any signature of a tree is equivalent to the all positive tree or all negative tree. And so you can eliminate every negative edge by resigning. So it is easiest to see with vertex one at a time. So if you resign here, this one becomes positive and this one negative, and then you resign as a leaf, and it is finished. So you can resign from up to down, and you get an all positive or all negative. Okay. So you have this intermediate step, and of course you have only positive edges, and you can have a sign-preserving homomorphism. Okay. So the idea of this closed-work preservation is that you don't need this sign-preserving mapping for the edges. It's more flexible, and it captures this equivalence somehow. You take any signature, and you can build your homomorphism. So this is why this new definition is proposed now. But of course, you can work with this one, which is equivalent if you deal with simple graph. So. Okay. So is it almost clear for this definition? I will keep it on this part of the board. Yeah.
In practice, it seems very much more complicated with the left one, because there are so many closed works.
Oh, in practice for checking, which is not, I am a theoretist.
I'm not talking about.
No, I see.
I'm saying in practice.
Yeah, yes.
Theoretist.
Yes, no, you're right. Yeah. If you want to check in practice, you have to use to find the good resigning somehow. Yeah, of course. No, you're right. But just I will just write you a lemma which links these homomorphisms of signed graph with the GERS, the 4 types of GERS we have seen before. So there is a well-known result in graph theory which says that when you have a homomorphism from G to H, so I can write it, it will be more clear. So considering ordinary graphs, if you have some homomorphism from G to H, you know that the chromatic number of G is at most the chromatic number of H, because if the chromatic number of H is some value, it means that you have a homomorphism to the complete graph with the same this value as the number of vertices, and just by composition of homomorphism, you get that. And you also know that odd GERS of G is at least the odd graph of H, where the odd GERS is just the smallest length of an odd cycle. Odd cycle. So this is not the usual GERS, which is the length of a cycle. This is always an odd number, and this is the length of the smallest odd cycle. And this is just because when you consider odd cycles, so I would just consider one case as an illustration. You can map the 5 cycle to the 3 cycle. You just color 1, 2, 1, 2, 3, for instance. But there is no homomorphism from the triangle to the 5 cycle. And this is for any odd values. You can go from the largest one to the smallest one, but not in the reverse way. And so this is why, as subgraphs, this gives you this observation. And so the idea is that we have exactly the same type of result for signed graphs using a chromatic number that I didn't define yet. So I will not speak about this chromatic number, but using all the types of girths. And the 4 types of girths are concerned with these inequalities. So we can state this result as a so-called no homomorphism lemma, which in fact gives you a sufficient condition for the non-existence of homomorphisms. For instance, here, if you know that the chromatic number of G is greater than the chromatic number of H, you know that there is no homomorphism. So this is in this spirit that we call this kind of result no homomorphism lemmas. And so we have, if G sigma as a sign graph admits a homomorphism to H pi, then so the girth ij of G is at least the girth ij of H for every ij in our in this set. Okay? So this is the same kind of characterization, which means that if you have some contradiction here, you know that there cannot be any homomorphism. Okay? It works also with these infinite values, and everything is fine. There is no problem. And so sometimes you may have if and only if. In general, of course not. Then. So obviously this is not true in general. Okay? But we managed to prove that for graphs with small maximum average degree, we have some kind of if and only H third. Yeah. So this is obviously wrong in general, but for some particular families of graphs, we may have this characterization somehow with if and only if. So I would like to speak about another things which is related to, of course, sign graph, of course, homomorphisms of sign graphs, but somehow why is it interesting to deal with these sign graphs? So this is in the first paper with Reza also. This is a subclass of sign graphs which has some particular interest. So I will deal a few minutes with this particular class, which is a class of signed bipartite graphs. So let me deal with signed bipartite graphs. Yeah. Yeah.
So for Dana graphs we got
no, sorry. I think I made the mistake with MAD and the value of the girl. Yeah.
Anyway, what
Yeah.
the value is for something lower value, bigger value. Do you know? I mean, do you know if that bound is tight of that?
Oh yes, it is. The H third is tight. Yes. Yes, yes. But I can tell you, but I have to check my document just to be sure. Okay. So let me just turn to signed bipartite graph, which means that this is a signed graph a graph with this signature, but G is bipartite. So it contains no odd cycle. No cycle of odd length. Okay? So in graph theory, ordinary graph theory, if you are studying homomorphisms, it is already not an interesting class. Because every bipartite graph maps to K2, is too colorable, it's not your favorite family if you are interested in graph coloring, of course. But in signed graph, it could be your favorite family. And somehow it is, but you don't know that it is. So, there is some kind of, it's not a good term. I will call that S operation. But S is not good. Oh, just consider that I am transforming some graph in a signed graph. So S is good. Okay. So you take your favorite graph, ordinary graph, which may be the triangle, for instance. And we are doing this famous S operation, which means that we are going to replace, so we have the original vertices of the graph, and we replace each edge by a 4 cycle. So each edge is replaced by a 4 cycle, which means that I add 2 new vertices for each edge, and I put a 4 cycle here, but a negative 4 cycle. Okay, so I replace each edge by this famous unbalanced cycle of length 4. You can put the negative anywhere, it's not important. So for instance, here. So this is G, this is S of G. So the signature, you just know that every such 4 cycle is negative. But all the possible negative signature of this cycle are equivalent. So, okay? Of course, this one is bipartite. So you take any graph, for instance, a non-bipartite one, you apply this operation and you get a signed bipartite graph. Okay? And so there is a theorem which somehow proves that this class of signed bipartite graphs captures problems on homomorphisms of ordinary graphs, which says the following. There is a homomorphism between 2 ordinary graphs G and H, from G to H, if and only if S of G maps to S of H. So this one is ordinary homomorphism, somehow. This one is signed homomorphism as defined before. You are in the corresponding class of objects you are dealing with. Okay? So if you have any problem in graph using graph homomorphism, you can translate this problem using this modest class of signed graph, which is only bipartite, but which is not so modest, in fact. We have also, there is also another result, because I don't think I will have time to speak about signed graph coloring, but you can, yes, I can discuss later. But as soon as you have homomorphism, you can define chromatic number, as Chagnik did before. You can say that the, let's say, signed chromatic number of a signed graph, G sigma, is defined as the smallest number of vertices of some graph H such that G sigma has a homomorphism, a sign homomorphism to H pi, some pi. Yes, there is a minimum, but it is written very, very so I try to. Okay, so of course the smallest order of a graph such that you have. So considering this notation, we can prove that, so another theorem says that the chromatic number of a graph, ordinary graph, is at most k if and only if yes. No. Let me just check, because I have several definitions of chromatic number, just to be sure. Yes. Yes, the chromatic number is almost k. No. So sorry, I'm just checking. What?
If k is greater than equal to 4, then the chromatic number of G would be equals to sine chromatic number of SG.
Yes, I'm not. No, I don't want to write something. I'm not sure. I prefer to check before. But there is some links between this particular class of signed bipartite graphs and this chromatic number. Yes, I have it. But so I want to write it. Okay, so this is the ordinary chromatic number is at most k, if and only if, for any signature, this sign graph maps to kk, so the bipartite graph k by k, with a matching as set of negative edge. So I will draw it just to be clear. So again, oh sorry, S of G. Okay. This is because of the hour. So S of G maps to. So again, we are in the class of signed bipartite graphs, because this one is bipartite, and it just means that, for instance, K33 with matching is a usual K33, but you put one matching of negative edges, and all other edges are positive. Okay, so you can reinterpret any question on the chromatic number of an ordinary graph as a question on homomorphisms of signed graphs. So you also capture this theory of graph coloring and graph chromatic number using this simple graph family. So they have also other things, as Chagnin mentioned, around this Adviger conjecture, which has an extension in terms, extension, not equivalence, which is more precise about the same kind of question, and of course many.
Is that the fourth Adviger?
Yes, or the Adviger conjecture. Yeah.
So basically, the whole undirected graph homomorphism theory
Yeah.
is particular
case of this, yeah, using a particular case mean restricted to this kind of graphs, not a subclass of bipartite graphs, because they have a special, yeah, yes, this is a very particular form of bipartite. So this is, yeah. So the bipartite, the whole class is something really more. And so there are many conjectures also on these classes of graphs. So, yeah. So I think this is a good point to stop because, yeah. Okay.